transcription has started. Okay. If anybody's ever curious, before I click record, we all get together and do a little vent session. So if you're ever feeling frustrated, want to get some stuff off your chest, join the live early, and we can vent a little bit, because I get it. I've been in y'all's shoes many times. So. Okay. So how is biochem feeling overall? How are we doing with the material? Are we on top of it? Are we behind? Kind of what's going on?
I am behind. It has become back burner and it makes me nervous.
Good. I'm glad that it makes you a little bit nervous. That's good.
I've been going through your videos, watching Ninja Nerd, and so in my head I think I got it, but as soon I haven't purchased the book, so to have the Linus questions always rocks me. I'm like, shoot.
Yeah, well, we're gonna crush through some Linus learning questions today. I figured out my issue last time. I was just on the wrong one.
Cool.
So we're gonna crush through as many as we can. And no, I'm not gonna make any promises, but I'm gonna try and at least record or mess with some of this stuff. You guys' exam is next week. What day?
Friday.
Yeah.
Friday for blended. Is it the same for?
I think ours is Thursday.
Oh, okay.
Okay. Okay. So what we might do is, if it's okay with everybody, I might swap the days of tutoring. So do biochem instead on Tuesday and phys on Thursday. So we get an extra biochem session in pre-exam.
I don't think any of us are going to argue.
Yeah.
Nope.
We'll plan on doing that. And also, I'm off all next week. I'm going to be at the beach.
Oh, shut up.
But I'll still have... Yeah. I get breaks too, guys. I'm going to spend most of my time writing my thesis paper. So, but as well, if I'll kind of check my schedule where things are at, and if we can sneak in a couple of mini sessions as well, I'll let everybody know ahead of time and kind of make that work. Cool.
Yeah.
Okay. Let's get started. Fatty acid oxidation and ketones. We went over this last week. I apologize, I didn't post that recording on the YouTube channel from last week. I'm going to do that right after this one. I'll post last week's and this week's, so those are available. So here are the questions. So a free form of a large chain fatty acid, a 16 carbon chain length, is activated for its catabolism. Catabolism, what does that mean again?
Breakdown.
Break it down, yeah.
Break it down. Which for some reason I think of like a dancing cat, but okay, breaking it down. Which of the following enzymes is required for its activation before the fatty acid is ready to enter into its catabolic pathway? We have fatty acid synthase, diacylglycerol kinase, acyl-CoA synthetase, or acetyl-CoA carboxylase.
My thought is acetyl-CoA carboxylase. I don't know.
And I was saying acyl
synthetase. Maybe.
My brain's still fried from yesterday.
That's okay.
Diacylglycerol.
That's why we're all here together. Okay. So looking at our enzymes, when we're talking about fatty acid oxidation, oxidation is the breakdown of all of these guys, okay? Where is my... And actually, we might have found our first typo in the Linus learning questions.
I swear we should get a refund every time we find one.
The following enzymes are required for its activation before the fatty acid is ready to enter into its catabolic pathway.
See, I always thought
I
thought that the activation took place with the carnitine, the cat 1 and 2.
Let's look at this. Watch this magic. Explain the following. Guys, if you're not using AI to help study, I promise you, like, don't use it to do your assignments for you. But like, it's so nice. Okay. So actually, we look at this. So to activate a free long-chain fatty acid, such as a 16-carbon chain fatty acid, the enzyme required is acyl-CoA synthetase.
Finally, something stuck. Sorry, I had to celebrate that.
Nice.
Acyl-CoA synthetase. When we look at the rest of the process, if we keep going, we'll see kind of the first step of breakdown of beta oxidation. That first step uses acyl-CoA dehydrogenase. And so we look at this, and actually we don't have a carboxylase within it. So there we go. Our acyl-CoA synthetase is what we're looking at. Our acyl-CoA synthetase. And actually, let me real quick. Acyl-CoA. I'm going to take our time a little bit through these just to make sure we really see what everything going on is. So, because this is we'll see the acyl-CoA synthetase come back in later. So the acyl-CoA synthase is typically, we think about it, we'll see it come back again when we look at the next chapter, chapter 2, more of like the biosynthesis type stuff. But wording of this question, super important. So the activation before it's ready to go into the catabolic pathway is that keyword. The synthetase is going to be activating the fatty acid. After 3 cycles of beta oxidation, the allelyl-CoA, so it's 18-1 delta. When you see a delta symbol like this, do you guys remember what that means?
Delta is always a change, right?
Typically, yes. When we talk about fats, that's telling us where the double bonds are. So
that would be like the 9th carbon or whatever, right?
Yeah. So unsaturated fat are poly and mono unsaturated fats. Typically, a fat looks like this, right? It's bound all the way across, and then on either side, you have a bunch of hydrogens coming out like that.
Mm-hmm.
And this one, when we call a fat saturated, when it has all of the hydrogens that it would need, it's saturated with hydrogens. So an unsaturated fat is going to look like this. Instead of having all the hydrogens, the 2 of the carbons have double bonds, just like that. And so that's when we see a delta symbol. That's letting us know on that 9th carbon, we have a double bond. So after 3 cycles of beta oxidation, remember beta oxidation is breaking it down, by how many would our 18-chain allelyl-CoA be shortened by?
6 carbon atoms.
Yeah, 6 carbon atoms. So we can look at this as well as break it down. Other ways you could say that is, how many acetyl-CoA would that be?
3.
Yeah, 3 acetyl-CoA have been broken off. So remember, each of them are broken every time that we perform beta oxidation. We break off 2 carbons. In order to fully break down allyl-CoA, how many cycles of beta oxidation would we need to perform?
9 or 8,
8.
Yeah, why is it 8?
Because the last.
because the 9th one would
cleaving.
be, there would be nothing left.
Exactly, because at the final one, so when we get, so the kind of the trick is the number of carbons, so number of carbons divided by 2 minus 1. That's a little formula to remember how many cycles of beta oxidation we're going to be making. Bam, 6 carbon atoms. Arrange the following enzymes participating in beta oxidation of fatty acids in the correct order. We have the beta hydroxyacyl-CoA dehydrogenase, thiolase, hydratase, and then another dehydrogenase.
I'm leaning towards C.
Why C? Walk us through it, Thomas.
The little acronym that he gave us, which was the D-HOT or whatever. So leading with the dehydrogenase, and then a hydratase helped me to just narrow it down. That was it. And the
Yeah.
thiolase is that final cleaving, as far as I remember. That's that final cleaving.
Yeah, good
Okay.
job. So we look at this. We have our dehydrogenase, then our hydratase, then another dehydrogenase, and then a thiolase. Kind of the big thing to remember here with a lot of these questions, the answers to a lot of this kind of stuff is going to start with either acyl-CoA or acetyl-CoA. If you look at a question and you have no clue what the heck it's saying, if it's talking about kind of like the beginning of something or like the start of any of the processes, like biosynthesis starts with acetyl-CoA. The enzyme that starts it is that acyl-CoA synthetase. Like a lot of our first answer choices are going to be the acyl or acetyl-CoA. So if you ever need to guess, lean towards those kind of answers. Okay. So remember D. Yeah. D-hot D. Dehydrogenase first, hot, and then another D in between the dehydrogenase. Carnitine is required to reduce NAD plus to NADH. True or false?
False.
So if you think about this in general, how many times have we looked at NAD plus being reduced to NADH?
Quite.
All the different things, all the different reactions that we've looked at, carnitine hasn't been present in any of those things. So no, we're going to be doing NADH. This is looking a little bit ahead to the future. When we talk about synthesizing our fatty acid chains, what are we going to use? What are we using? Oh, what's it called? It's not a, yeah. What are we using as one of our coenzymes? Do we use NADH or NADPH when we synthesize?
NADPH.
NADPH.
It's NADPH. Think way back to Biochem 1. What were some of the ways that we got NADPH? Specifically, there's one big one that we really hit hard, and I told you many, many times, hey, don't forget this because it comes back.
This is the pentose phosphate pathway, isn't it?
It is. Really, really good job. That pentose phosphate pathway gives us the NADPH that we need for fatty biosynthesis. Good job. That'll come back around. Carnitine is one of the amino acids found in protein, an essential cofactor, a 15-carbon fatty acid, or essential for intracellular transport of fatty acids.
D.
It is, in fact, D. Carnitine. I always think you find a nice videos.
And that's to transport the fatty acids into the mitochondria, right? I think.
Let me pull. There's a nice little. Yeah, so carnitine's job is transport. What's the? Carnitine specifically is found inside of the cell. Okay, so carnitine is responsible, and we'll get to all of this. You see all of this kind of stuff: the carnitine, the CPT1, CPT2 for moving. Because if you remember, beta oxidation. Where does beta oxidation take place?
The mitochondria.
Yeah, inside of the mitochondria. So we need ways to get those long chain fatty acids into the mitochondria from the cytosol. So that's carnitine's job. Carnitine's job is to help the long chain fatty acids get inside of the mitochondrial matrix in order to be broken down. And then when they're broken down to acetyl-CoA, finally, remember acetyl-CoA, when we talk about like glycolysis and stuff, where does acetyl-CoA go into? How do we get energy out of acetyl-CoA?
The Krebs cycle.
Through the Krebs cycle. Yeah.
And where did the Krebs cycle take place?
That's also in the mitochondria.
Also in the mitochondrial matrix. Yeah, so we make it easier on ourselves. We get that fatty acid using carnitine into the mitochondrial matrix. So that way we can break it down every time that we break off those two chunks, turn it into acetyl-CoA, and then once it's acetyl-CoA, it plugs into the Krebs cycle, gives us our 3 NADHs, our 1 GTP, our 1 FADH2, which then continues off into the electron transport chain.
Awesome.
That's the job of carnitine. The other protein that we're thinking about that also does transport starts with a C. I'm spacing on the name right now. It is the chylomicron. That's what it's called. The chylomicrons are the ones that are acting in that lymph system that are carrying the fatty acids from the intestines into the blood to get them to go like to the liver and to where they need to go. Okay. Complete beta oxidation of 1 mole of which fatty acid would generate the most ATP? There's going to be a handful of questions like this. I'm pretty sure in his slides, he has a list of the fats that he kind of wants you to know. I think it's in this one. I know it's in one of these. Come on. I think you guys have looked at these more recently than I have, but
yeah,
in one of these, he has a handful of specific fatty acids that he kind of has circled and they're like blocked in the specific ones that he wants everybody to remember. I can't find where they are. They're somewhere through all of this. I know that they're in there somewhere.
Oh, I found some. There's like a palmitoleic acid, oleic acid.
Remember which presentation it's in?
So I'm in the textbook on page 26.
Actual page 26 or 26 of the PDF?
Actual. Yeah.
Okay, yeah.
Is that what we're looking for?
Yeah. A handful of these ones. Palmitoleic, oleic acid, linoleic, arachidonic
Stearic.
acid. There's another, I know that there's another, he has like a handful of fatty acids like blocked off somewhere with like that tells you the specific number. I can't find exactly where that is. I know that it's within the material somewhere, but that's okay. When looking at the Linus questions, any of the ones like specifically these types of questions that he's going to ask you guys, we'll focus just on these ones and remembering these specific ones. So how many carbons in? We should know palmitic acid is usually the most common one. That one is super important to know. It's 16 carbons. Butyric acid has 4 carbons. Propionic has 3 carbons. And then stearic is in 18 carbon. I know he has, it's either in the book or in one of his slides somewhere that he has this. If I'm not mistaken, I'm pretty sure this exact question is gonna pop up on your exam. Just note, most of the time he likes palmitic acid. Palmitic acid is a big one. It's super, super important. It's one of the base fatty acids that our body produces. But in this case, stearic acid has 18 carbons. So I would remember, especially the bigger ones, palmitic acid, stearic acid. If we come across any more, make sure to highlight those and make sure that we keep those in mind. Fatty acids are converted to their coenzyme A esters in the reaction catalyzed by which of the following? First off, the coenzyme A esters. What the heck are those? These are going to be the intermediates kind of in the lipid breakdown. Okay. And if you remember our first step that we mentioned way back in question 1, what's our starting point for breaking down the fatty acids?
Is activated by that, what was it, acyl-CoA synthase?
Exactly. So it's the same question as question 1, just asking it in a different way. We talk about coenzyme A esters. Those are the intermediates in the lipid breakdown. So breaking down, because remember, all in the book, we look at beta oxidation, all of the products of beta oxidation. So each of these guys, palmitoyl-CoA, enoyl-CoA, hydroxyacyl-CoA, those are all coenzyme A esters. Okay. They're called coenzyme A esters because the coenzyme A is bonded with an ester bond to the rest of the stuff. Yeah, you did. That's fine. This is another way. So if you ever see coenzyme A esters, that's all it's referring to. It's referring to other stuff that has the coenzyme A bound to it as well. That okay? That feel okay?
Yeah, wouldn't it be fair to say that you could like an equally accurate term would be coenzyme A thioesters? Because usually, from what I remember, esters have like an oxygen as that connecting bond, but in this case, we're having a thioester because of the sulfur on the CoA.
Yeah.
Would that be?
Yeah,
as
you could
far as
say you could probably say ester. You could also say thioester.
Okay.
Just if you see it written in that kind of format, coenzyme A, esters, thioesters, whatever, now you know what it's referring to.
Okay.
And it's specifically referring to
What's bound
all
to
of
that
these
coenzyme A? Yeah.
components
Okay.
continuing of the beta oxidation. For each acetyl-CoA that is incorporated. Okay, so this is where it gets a little bit annoying because now we're looking at synthesis instead of oxidation. So we kind of, Linus is mixing the two. So we're actually, I think, we'll answer the question, but we'll loop back around to this when we actually look at biosynthesis stuff. So for each acetyl-CoA that is incorporated into a growing fatty acid, what energy inputs are required, assuming that the growing fatty acid contains at least 4 carbons? So with this, answer is going to be 2 NADPH and 1 ATP. With the synthesis, we don't really mess with the FADHs, so
Nice.
we'll look at that again later. It's in the wrong place. Good job, Linus. Free fatty acids in the blood circulation are A, bound to hemoglobin. What's the main thing that binds to hemoglobin?
Oxygen.
Oxygen. So it's busy. It's not going to be grabbing fat. Carried by the serum albumin, bound to carnitine, or freely soluble in water phase, present in the blood. Remember carnitine, we talked about carnitine. Where's carnitine located?
Intracellular.
Yeah, that's our intracellular, helping it get from the cytosol into where?
The mitochondria.
Into the mitochondria. So now we have 2 options. It's either freely soluble in the water phase present in the blood, or it's carried by the serum albumin. Now, fat, right? Oil and water, or fat and water, don't really mix. So if it was just floating freely in the water, in the liquid portion of the blood, it would literally just rise to the top, crust all over our arteries, and we would be in trouble. So it's going to be carried by our serum albumin. You'll learn, this is more towards the end of physiology. You'll talk a lot about albumin. Albumin is super, super important for a lot of reasons. One of those being that one of the main things that keeps our blood inside of our arteries, kind of inside of our whole circulatory system, is albumin. It creates a big difference in concentration inside of the blood versus outside, which allows, which causes a lot of like the water and stuff, and the when our circulation is going through, and we push fluid out of our capillaries and stuff, it's what really helps maintain our blood volume and helping us to suck stuff back into the cells. So that's like towards the very end of Phys 1, you'll talk a good chunk about albumin. So just
not to get too far tangential, but like if somebody had low albumin levels, would they be predisposed to edema?
Yeah.
Yeah.
And you'll talk about so even, ma'am, so without albumin, fluid leaks out of your blood, builds up in your lungs, abdomen, belly, or other parts of your body. Albumin is also produced inside of the liver. So people who have liver issues, liver failure, that kind of stuff, tend to have low albumin, which is why people with chronic heart disease, chronic liver failure, that kind of stuff, tend to be really, really swollen, really, really puffy. They get something called pitted edema. Pitted edema is when you like poke into it and it squishes, take your finger away, and the impression stays there for a while and just like slowly fills back in. It leaves a pit when you poke it. Okay, next question. Oh wait, little thing at the top there. How many cycles of beta oxidation are required for the complete oxidation of stearic acid? So it's 18 so 18 carbons. How many cycles of beta oxidation do we need?
Eight cycles.
Good. Remember, what was our formula that we talked about? Number of carbons divided by 2 minus 1. How many total molecules of acetyl-CoA can be generated through the beta oxidation of 1 molecule of palmitic acid? Remember, we talked about palmitic acid. How many carbons does palmitic acid have?
16.
Yeah, 16. So how many total cycles of beta oxidation are we going to be performing?
6.
7.
7 cycles of beta oxidation. Because remember, it's 16 divided by 2 is 8 minus 1 is 7. How many total molecules of acetyl-CoA are we producing now?
8.
Good.
Because there's two carbons per acetyl-CoA pulled from the fatty acid chain.
Mm-hmm.
Okay.
Yeah, and I'd misspoken a little bit last week. If we have an odd number to start with, our last 3 carbon that we have, so we'll cut off all the way until we have 3 carbons, and that's a malonyl CoA that we produce. If we start with an odd number, so like if we started with 17, and we would then produce 7 molecules of acetyl-CoA and 1 molecule of malonyl CoA. I had misspoken about that last week, so I wanted to make sure I corrected that. We don't talk about that a lot, but just in case it does come up. Identify the ketone bodies formed during severely starved condition. So this is kind of the severely starved condition. It doesn't really need to be there. It's just adding extra words. Because ketone bodies, what's the purpose of ketone bodies? Why do we form ketone bodies?
It's like oh yeah, you go ahead.
Oxidize the fat to make it usable as energy.
Yeah, so to make it usable as energy. Why though? Like, what led up to that point? What have we already done up to that point before we start producing our ketone bodies? What state is our body in?
Ketonic,
yeah. So essentially, when we produce ketone bodies, it's because we're completely out of glucose. So one of the ways, obviously, we have like gluconeogenesis and those other processes, but a lot of those, can take time, and they're not always super efficient. So another method that we have is we use our we go into ketosis, where we produce these ketone bodies in order to continue to feed the brain. And all 3 of these, this acetone, beta hydroxybutyrate, and acetoacetate, those are all examples of ketone bodies. Next question, identify the ketone body. We just saw this. Cholesterol is not a ketone body. Stearate is just the fat. Mevalonate is another fat. So acetoacetate is our ketone body. So be able to recognize these 3. You'll have questions just like this. You'll probably have 1 or 2 questions that's just like identify which one is a ketone body. In the mitochondrion, as a blank moves from the inner membrane space to the matrix, blank is transported in the opposite direction. So we're talking about the mitochondria. Specifically, we're talking about, the movement of the fatty acids and stuff going from the cytosol, then into the intermembrane, and finally into the matrix.
I totally just spaced that. What did you say? I'm sorry.
You're good. So this is talking about mitochondria. This is the mitochondria. So in the mitochondria, we're moving some type of fatty material from the cytosol into the intermembrane space, and then finally into the matrix. Pull up the... Where'd my pretty graph go? There it is. Here's our pretty little graph. Right, so we have the carnitine acyltransferase 1. So we start with a fatty acid, in the mitochondria as a blank moves. So we're talking about the intermembrane space. So we've already done this step. So we're looking at the intermembrane space, going from the intermembrane space to the inside. Here we're dealing with our carnitine acyltransferase 2. The job that we're doing is we're taking carnitine and going out in order to bring a fatty acyl carnitine. So it's bound. You'll see the carnitine comes in and it binds to this, or all this, our CoA binds onto the carnitine, and then it comes back inside to do its whole thing. Carnitine and the fatty acyl CoA combine and form carnitine fatty acyl esters, also known as acyl carnitine. That's done by that first, we'll call it CAT, carnitine acyltransferase 1. And then
On a side note,
passes
that's the question Dr. Sarkar put me on the spot with in our live like 2 weeks ago.
Yeah, so this
I couldn't
question
answer
right
it,
here,
Kat couldn't answer it, neither could Cheryl. We were just like,
yeah, a lot of biochem 2, like, there's just a lot of words with biochem 2. A lot of big
where I'm
words.
lost with biochem too. Is
Yeah.
I'm like, there's so many things that it's so many words.
The trick to that, between now and your exam, what I recommend you do is either watch Sarkar's lecture, or go ahead and you can watch my recordings of going through the book, right? Or even rewatch the LINUS question videos. Every single time you get to a word that you don't understand what it is or where it's coming from, pause, look it up, write it down. Like, pull up the LINUS learning questions, and as we go through, like, fatty acyl carnitine. What the heck is fatty acyl carnitine? Pause, figure it out what it is, either by looking at the book, looking through Google, doing something, and then write it down. Carnitine, what is carnitine? Okay, carnitine is this thing. Mitochondrion, that's a weird word. Why is it mitochondrion instead of mitochondria? Just because it's the fancy way of saying mitochondria. So anytime that you see a word that you don't know, look it up. And what you'll notice, you'll probably end up looking up the same words as you keep going through questions. You'll probably look up the same words 2 or 3 times. After that second, third, or fourth time that you need to like recheck a word, either by like re-looking it up or like scrolling back up, you'll start to get a much better grasp of what everything is saying. Okay, it takes some time and it sucks, but that's really like the only way to do it, unfortunately. Okay,
Yeah,
so
especially once we're doing like the fatty acid synthesis, there's like these complexes and they have all these different regions. Ugh.
just like in Biochem 1, difference between Biochem 1 and Biochem 2, Biochem 1, you had a lot of long processes that occurred. Glycolysis was the 10 different steps. Krebs cycle was a mess of steps. Electron transport chain was a whole bunch of different steps. Biochem 2, there's a lots of little things that are 2 to 5 steps that we then need to know, and we need to kind of sort them out to keep them straight. Because they're all important, they play different roles. It's not as much of like big steps, big long chains of steps. So the major site of formation of acetoacetate from fatty acids. What is acetoacetate?
A ketone.
Good. Where do we produce our ketones? Let's think about this logically. What organ in our body is responsible for making sure that there's a good distribution of the stuff that we need for energy?
Liver.
Liver.
Nice.
The liver handles all of the blood glucose stuff. It also handles, making and distributing those ketones. If you also can think about it, a lot of times, a lot of stuff is stored in the liver. Have you ever heard of something like fatty liver disease? Because it's the same thing. The liver plays a really, really big role in transporting, and getting the fat to all of the different locations and getting energy to all the different places. So one of the first places, organ-wise, that we're going to build up fat is where we deal with storing all the energy. So in the liver. Oxidation of fatty acids are endergonic or exergonic. So oxidation, is oxidation the breaking down or building up?
The breaking down.
Yeah, when we break stuff down and we break bonds, is that typically endergonic or exergonic?
Hexer.
Yeah, exergonic. Which then it just goes to say synthesis of fatty acids is most likely going to be what?
Endergonic.
Good. Oxidation of which portion of a phosphodieacylglycerol molecule produces the largest amount of the biologically available energy? So we look at these words, right? Oxidation, breaking down. Phosphodieacylglycerol. So we're looking at this molecule, a phosphodieacylglycerol. What the heck is that?
Kind of like a it's not quite a triglyceride, right? Because it's diacylglycerol. Is that true?
Yeah, correct. Because triglyceride is 3, right? So we have 2. So kind of what we're gonna have, we have like our glycerol backbone. We have 2 fatty acid chains, and then our phosphate group off of it, like that. So we have glycerol, we have phosphate, and the diacyl are our 2 fatty chains. So we have glycerol, we have fatty acid, and we have phosphate. So of those 3, breaking down each of them, where do we get the most energy from?
Definitely the fatty acids.
Definitely the fatty acid. See, so if we take the time a little bit, kind of break down the question, break down all the words and think about it. It's not as complicated a question. Big words, not as complicated of a question though. Big words makes my brain hurt, so. Okay. How are we doing up to this point?
So far, so good for me.
Okay.
I do have to go in a little bit, so I'll just hop off.
Yeah, just whenever you gotta go.
Okay.
We'll just keep going and I'll record and post right after.
Awesome.
Question 18. Predict what could be the effect of oxaloacetate concentrations on the production of ketone bodies. So if we stop real quick and we think about it, oxaloacetate, what is oxaloacetate? Where are we getting it from? What does it do? What's its purpose?
It is a byproduct of the like it's involved in the Krebs cycle, but it also can be part of the transport into and out of the cell with that malate aspartate shuttle system.
What's the whole purpose of that shuttle system?
Movement of, was it NADH into the mitochondria?
Yeah, NADH from where?
From the cytosol.
Yeah, what was producing the NADH in the side of the cytosol?
It would be like the byproduct of glycolysis.
Yeah, right. So we're thinking oxaloacetate, main things is going to be part of that transport if we're performing glycolysis, as well as if whenever we're doing the Krebs cycle. It's that going back and forth. As well, if you think about it, oxaloacetate is one of our other, it's one of our intermediates that we can also use gluconeogenesis, plug it back into stuff, mess around with it, and spit out more glucose to help us keep producing stuff.
Okay.
But if we look at this and say, okay, if with oxaloacetate, we start to think, if there, let's say, if there's really, really high levels of oxaloacetate, so we're producing a ton of oxaloacetate, what does that say about our body, about those processes, about kind of what's going on?
That we're like flush with energy, like lots of glucose is available.
Yeah, we got tons of glucose. If we look at the answer choices, high levels of oxaloacetate would enhance production of ketone bodies. So right away, we look at that. I'm going to go with no, because with lots of oxaloacetate, that means we have a lot of glucose. We're running through glucose. We're producing energy like crazy. We're good to go. So we have no need of ketone bodies. So levels of oxaloacetate does not have any effect on the production of ketone bodies. We know that that can't be true as well, because oxaloacetate, production of oxaloacetate is directly linked to glucose being broken down, going through glycolysis and the Krebs cycle. So our last answer choice, that really low levels of oxaloacetate, is going to encourage the production of ketone bodies, because that means we're in a state where we're not running through glucose. We either don't have a lot of glucose, or for some reason we're not breaking down glucose. Cool beans? The enzymes for oxidative degradation of fatty acids are localized within where? Where does the fatty acid oxidation take place?
Mitochondrial matrix.
Yeah, our mitochondrial matrix. I mentioned this very, very briefly. Where does synthesis occur? Remember? Maybe I didn't mention this. Synthesis occurs in the cytosol. So when we get to synthesis, look for it in the cytosol. Oxidation, the breakdown, happens inside of the mitochondrial matrix, because that way we can feed it right into the Krebs cycle. Cytosol is going to be the place where we synthesize our fatty acids. The fatty acyl-CoA dehydrogenase reaction. So we look at that reaction, fatty acyl-CoA dehydrogenase reaction. Where does this reaction take place?
Is that in shoot?
Like it's at the beginning of the holy cow, just lost the word. Of the breakdown process.
Yeah, our fatty acyl-CoA dehydrogenase right here. Bam. That's our first step, our first real progression step of beta oxidation starting. where we start to break stuff down. It is, going back to the big words, it is that word doesn't look right. Analogous. That word doesn't look right. Whatever. To the succinate dehydrogenase. You know, remember when you stare at a lot of words, for some reason, like some of them start to look wrong. That's fine. Is analogous, or it's comparable to the succinate dehydrogenase reaction. Identify the active form of the vitamin, which is used as a coenzyme in both of these reactions. So this portion right here, the succinate dehydrogenase reaction, is kind of an extra tidbit. It's not necessary to answer the question. It's more of just a helpful hint of like, hey, if you don't remember this reaction, but you do remember this reaction, you can figure it out. And kind of what we just saw at the book, we're using FAD. Boom. We have FAD coming in, getting reduced to FADH2. FAD is our active form for this reaction, and it acts as the coenzyme.
That would have thrown me off completely, because I'm like, the only one that's a vitamin there is biotin.
So remember NAD and FAD? The N, what does the N stand for?
Niacinamide.
Yeah, so
Didn't know
niacin.
Didn't remember that at all.
Yeah. And then FAD, what does the F stand for?
Folate.
Folate?
So it's actually a flavin. FAD. Oh, man.
Drake, you gotta remember our brains are fried.
I know. That's fine. That's fine. I asked the question. I'm not fully expecting you guys, that's why I'm asking the question, just so that if at any point, like, you don't know the answer, that's completely fine. I don't care if you guys don't know the answer. I'm doing my best to get you guys to think.
At least you don't care if we don't know it, because
Dr. Sarkar gets a little upset.
And some of
he gets frustrated
that I've used are like frustrated about it when I don't, and I'm like, that's why I'm here.
Exactly. Like, I don't know. This is a safe space. I don't care. Like, I'm fully expecting, honestly, the way that I see it, if somebody can't answer a question that I'm asking, it's either one, because it's a sucky question and I need to rephrase it, or two, you don't remember. I mean, you're being bombarded with 8 million things every single day to try and remember. So, like, I don't care if you don't remember. I'll explain it 1,000 times as long as you're trying. Like, I don't care. So flavin is another form of riboflavin, which is one of our B vitamins.
And
you remember?
I can remember which one. Hang on.
What's our mnemonic for our B vitamins?
Tall, rich, nudists played pickleball for centuries.
I made that mistake last week. Pickleball. Separate out into 2 words, so you don't forget that it's 4 centuries. Yeah, so our niacin is our B3. Rich is our B2. Riboflavin is our B2. FAD is our B2 vitamin.
Because it's 1, 2, 3, 5, 7, 9, right?
I always remember 9 and 12 are last.
Okay.
And then we have 1, 2, 3. There's 5, 6, and 7. 1, 2, 3.
Okay, so 4 is the one. 4 and 8 are the ones that are like not in there before 12. Okay.
Let me just double check. Yeah. 1, 2, 3, 5, 6, 7, 9, and 12.
Cool.
Don't worry, my brain is also exhausted. So I don't expect perfection of you guys as long as you don't expect perfection from me. So next question. And actually, before we move on to the next question, let's just really quick just talk our way through this really quick. We start off with our fatty acid that has a CoA. So this is going to be what we're talking about, kind of an acyl CoA. Remember, we talked about the difference between an acetyl CoA versus an acyl CoA. The acyl CoA is more like the broad term. It's essentially like any of our fats and stuff, no matter how long they are, with a CoA attached to them. Acetyl CoA is the specific 2-carbon form of it, right? Ring a bell from last week a little bit?
A little bit.
Yeah. So our acyl CoA dehydrogenase, and then we have our FAD. It gets reduced. So we're taking away some hydrogens and stuff away from our fatty acid, and that turns it into trans delta 2. Remember what this delta means when we're talking about fatty acids?
So the double bond.
Yeah, we have a double bond. So right there, that double bond at that 1, 2 carbon. It's an enoyl CoA, trans enoyl CoA. Then we have our hydratase. Hydratase, hydro, we need water, so we bring in water and add water to it. It's an L-beta hydroxy acyl CoA. Hydroxy now, because we added water, it's hydrated, so now it's a hydroxy. Then we dehydrogen again. Anytime that we see a dehydrogenase, we're removing hydrogens, and we need a place for those hydrogens to go. So either we're going to have an FAD or we have an NAD, because something needs to be accepting those hydrogens. So if you have to guess, if you see a dehydrogenase, remember, guess either the NAD or the FAD. So we have another dehydrogenase. And then finally, we have an acetyl transferase, aka a thiolase, which rearranges all of the good stuff. And we get an acetyl CoA, like cuts it off. We get an acetyl CoA released, and then our new acyl CoA with 2 less carbons. And then we repeat the whole process all the way through. Wanted to walk it through really quick in case we get some more questions in the future. So the following fatty acid, in which the indicated carbon is labeled with 14C. So there's 14 carbons. It is going to be fed to an animal. That's not a question.
I'm like, huh? What?
Apparently he wants to know what 14CH3CH2 9COOH is.
That's my guess. The answer is propanol-CoA.
Thank you.
That question's on
Cool.
crack. So,
Can you just put a big ass line through that, please?
Can we not worry about that
But I'm
one?
gonna laugh if it's on the exam.
Oh my gosh, if that's on the exam, I might cry.
ooh.
Either that or
Or I'm gonna
Liz
get it
and I
right
are gonna be like,
immediately.
what the fuck?
Let's double check this and see if.
What the fudge? I'm like, that question doesn't even act as a question.
I'm like, yeah, that question's not even a question.
Oh wait, hold up. There's supposed to be the rest of the question. Hold up, let me see. This is supposed to be the rest of the question. After allowing 30 minutes for fatty acid beta oxidation, the label would most likely be recovered in...
The label doesn't make sense.
I'm like, I still don't understand that, but cool. That would be
Let's
one.
see.
If it shows up, I'm either just going to remember the answer or I'm going to take an L because I don't get it.
Yeah, I don't know.
I'm gonna take an
Go
L
away.
or just remember it's PO.
Seriously.
Yeah, either just remember it's propanol CoA, or yeah, I don't know what the heck's up with
What?
that. The site of beta oxidation of fatty acids is the mitochondria, the plasma, the cytosol, or the endoplasmic reticulum.
Mitochondria.
Unreal.
Good job.
Whoa.
What happens in the cytosol again?
I'm like the glycolysis. I don't know. One of those
Like
other
the
processes.
Glycolysis does,
The
but also
other.
remember our fatty acid synthesis.
I hope it just
Right.
popped.
The endoplasmic reticulum. I'm gonna throw in a little bit of fizz just because help us remember
Please do.
stuff.
Please
Oh,
do.
thanks.
What is held inside of the endoplasmic reticulum? What's the main cation that it holds on to in order to release? Yeah, holding on to calcium. The endoplasmic reticulum, kind of its cousin in the muscle, what's that called?
The sarcoplasmic reticulum? Wow, I actually remembered something.
What's the name of the voltage-gated sensor in the T-tubule that's connected to the sarcoplasmic reticulum?
Ranidine?
Ranidine thingy-madoody.
So we have the
Or it's
ryanidine
the
receptors.
it's the DHP, Ooh.
Yeah. So remember DHP, the question was asked about voltage. DHP is our voltage sensor. Ryanidine receptors,
right?
those are mechanical. Good. Dope. The transport of fatty acids from cytosol to the mitochondrial matrix requires which of the following?
ATP, carnitine, and coenzyme A.
Yeah. Boop.
Woohoo! Remembered another one.
Let's take a second real quick. I think it was down here. Nope. Higher. Doop, 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 doop. Here we go. Here
That
we
was
have... So here we have our carbon source. So this right here, I'm going to do this because this guy right here annoys me. I think he is more confusing there than he is helpful. So this guy right here with the R group, this guy right here with a sulfur CoA with a bioester or ester bond attached to it. What do we call this fatty acid chain with a coenzyme A bound to it?
I don't know.
Your acyl-CoA?
Good, our acyl-CoA. So that acyl-CoA, that whole thing, is going to be passed along to the carnitine. So it let the CoA lets go, passes it off to the carnitine. The carnitine uses the carnitine acyltransferase 1 because carnitine is now bound to an acyl, and it transfers it across the membrane, and it's the first one that does it. So it transfers it from the cytosol into the intermembrane space, and then we have another transporter protein with a carnitine acyltransferase 2. So it comes into the matrix, and then that carnitine gives that fatty acid, that acyl-CoA, or just the acyl in this point. It's going to hand it back to another coenzyme A. So that way we end up, once again, with an acyl-CoA at the end, thanks to carnitine, thanks to the carnitine acyltransferase 1 and the carnitine acyltransferase 2. And also our coenzyme A. Where's the ATP used? In one of these steps, ATP is used. Probably forming of bonds or breaking bonds or something. I don't know. The book doesn't say anything about ATP, but probably somewhere in there ATP is used, is my guess.
Thank you, Drake, for reminding us we don't have to remember this all at once.
Seriously.
Like, yeah, I don't know. It says ATP, but I don't see ATP. I don't know. It's fine.
Only reason I remembered that one question is because it was a quiz question.
Yeah. So, but you know, we can look at these other answer choices as well, and that's why I want to. Like, I'm gonna take our time, go through each of these processes, through each of these doohickeys. Just so the more times that we look at them and break them down slowly, the better off we're gonna be, and we'll get there. That's the point. Hopefully, we'll get there before next Thursday. That's the goal. What is the
Because I do better than I did on Fizz, I'm happy.
Liz, as long as I get a C in biochem, I do not give a flying fig what happens.
A flying fidoodle. What is the correct order of function of the following enzymes in beta oxidation of fatty acids? We've seen this question before. It's back. What was our little mnemonic, or what were the letter system that we did?
I know it starts and ends with a dehydrogenase, but I don't remember the two in between.
D-hot. DHTD. Is there a better way to remember that? I don't know, nothing comes to mind right away. So we look at this, and we always remember whenever we're talking about the first thing that we care about the most, what's one of our first answer choices always going to be? And what's always like the first step? It's either going to be acetyl or acyl. That's always what we look at first. So 4 is going to be always acyl. The acyl-CoA dehydrogenase is always going to be our first one. So immediately we eliminate those two. So dehydrogenase, and then our hydratase. So 3 has to be next. So bam, can't be that one. D is the only choice that we have left. And that's the correct answer. Nice.
That's probably going to be an exam, knowing him.
Oh yeah. He'll have.
If he asks it more than once on the Linus questions, it will be an exam question.
Oh yeah.
I'm pretty sure he did proofread when he made the Linus questions, so yeah.
I don't even know if he made the Linus questions. I don't know. Maybe I think somebody else might have made them, and then he just kind of approves them. Because here's a repeated question. What is the effect of oxaloacetate on the production of ketone bodies? Remember this one?
Variables enhance the production.
Yeah. What are our 3 ketone bodies? Do you remember the names of those?
Hydroxybutyrate. That's one of them.
Acetone. And it's close to acetone. Like the name is like close to it. Aceto.
Acetoacetate.
Yeah, that's it.
Acetoacetate. Beta hydroxybutyrate, the acetoacetate, and our acetone.
Why can't our exams be low stress like this? Because I could totally do exams like this.
Just me reading you the questions, just like,
yes.
Yeah.
And why does it have to be so hard to get our dang frickin' accommodations?
Because life sucks and then you die. Kidding.
Oh,
kidding.
this is true.
That's what my grandmother used to say. So.
Yeah.
Well, here's the thing. I think I joke with mine because mine's traumatic brain injury. Mike Parker has the traumatic brain injury clinic, so they know what the hell we deal with. Sorry, I'm tangenting for a second. Mike, you guys know the challenges we face, so why make it harder? If you guys know the accommodations help us, approve them.
Yeah. So mine's a super little thing that I want to try to get, but I don't think I'm even going to try. I'm just going to work around it. Because mine is like, because they don't, when we take this stuff on campus, they're like, you can't have a water bottle, you can't get it at all. And I'm like, I have chronic kidney stones. If I need a water bottle and I need to be able to get up and go pee if I have to. But I'm not going to fight that fight. I'm just going to deal.
If anything, like, I recommend speaking with your professors specifically. Like, if the professors know you have a specific issue and also, you know, because you might be able to accommodate in a different way. Like, instead of taking the test in like the room with everybody else, a lot of times like they'll put you in, like, there is like a little testing center on campus that's like monitored. So I mean, like, there are other options. So it might take some time and it can be stressful, but if you genuinely feel like it's either going to improve greatly, if it's going to improve your quality of life as well as improve your ability to learn and, you know, not hate life, give it a try and try and get through it. And again, even if it takes time to get it all through, you know, once it gets through and it gets approved, you know, you're in a much better position after the fact. So I know it can be frustrating because I did the same thing where I often thought about going through that whole loop and process, but just didn't want to deal with all the jumping through the hoops. So okay, I hear you guys though. Next question. What is the function of the hormone-sensitive lipoprotein lipase enzyme? Hydrolysis of triacylglycerols of plasma lipoproteins to supply free fatty acids to different tissues. It synthesizes triacylglycerols, degradation of lipoproteins to supply amino acids, or it increases intestinal uptake of various fat molecules.
I could be entirely wrong, but don't lipases break stuff down?
Yeah, specifically, what do they break down?
Triglycerides in this case.
Yeah.
Or A
Fat.
lipase breaks down lipids.
Yeah.
If it's a lipoprotein, it's got lipids and it's got protein in it. So, so
Which
it's a lipoprotein
makes
lipase. Yeah.
think that it's going to be C.
So we look at this, right? So lipoprotein lipase, real quick. Bam. So our lipoprotein lipase is an extracellular enzyme. Enzyme is predominantly in a couple different tissues, adipose, muscle, heart. Lipoprotein lipase functions to convert triglycerides to fatty acid and glycerol. Okay? So it's going to be breaking down the triglycerides. So if we look at this specifically, the purpose of breaking down a triglyceride, right? The triglyceride has a glycerol and 3 fatty acids, right? So when we break this down, what do you think the body would probably be more likely to need if we were to break this down? Does it more likely need the glycerol, which is the protein part, or the fatty acids?
The fatty acid.
More likely the fatty acids. And when we look at this lipase, lipoprotein lipase, lipoprotein, this is describing what it is, that it's a lipid protein mix, and its job, lipase, is to break down fat. So the answer for this one, while C, the degradation of lipoproteins supply amino acids, is a technically correct answer, where it does break down other lipoproteins because it's glycerol, triglycerides. The main reason is not to supply amino acids, but to supply the free fatty acids. So A is going to be our best answer choice for this.
So is this one of those instances where an answer may not be the best answer?
Correct. Yeah. Where so degradation of lipoproteins, like while it does just break down, which is a typical definition of degradation, it's not to supply the amino acids, because it's even like when you say amino acids, technically it's only one amino acid, it's glycerol. So that part, like this part is correct. That part is the second piece is not. So that's why the first part is to supply the free fatty acids. That's our main reason for breaking down triacylglycerols, aka triglycerides. Remember, those mean the same thing. To supply those free fatty acids. Does that make sense?
Yes.
Cool. I feel like this is really going to be a question, but we'll answer it. Which compound is an intermediate of the beta oxidation of fatty acids? So we think about, first thing, fatty acid, beta oxidation, right? Our very first step. Actually, let's back up a little bit. The very, very, very first step, the activation, right, that we talked about way in the beginning, activation of a fatty acid is done by what enzyme? Okay, if we don't remember.
Acyl-CoA.
Acyl-CoA synthetase.
Good. Activation of the fatty acid is by acyl-CoA synthetase, which, if we remember, we look at now, acyl-CoA is just a fatty acid with a CoA attached to it. So we realize now, okay, we need the synthetase, we need to create the acyl-CoA. with the synthetase in order to get to the next step to actually get it into beta oxidation. Because to start beta oxidation, we need it to be an acyl CoA. Because once it's an acyl CoA, then the carnitine can be used to transport from the cytosol to the mitochondria, to the matrix of the mitochondria, and then starts beta oxidation. Took us a little while, but we finally got there. Does that flow make sense? Kind of why each step, now that we've talked about, needs to happen?
Makes more sense than it did, yeah.
Yeah, it's all coming together. So immediately, we look at these steps, right? To be an intermediate of beta oxidation, let's look at each of these and say, what has to be included in each of the intermediates of beta oxidation? What's one of the things that connects all of them, that it's the same in all of the intermediate steps?
The CoA.
The CoA. So immediately, your band and your band, gone. So let's keep looking now at this next two and determine, okay, which of these two potentially could it be? CH3, CO, CH2, COS, CoA, here. This next part, I'm not entirely sure. Honestly, not entirely sure, because even like with the book, I don't really recognize and understand exactly why this is. This one is the correct answer right here. My best guess is because if we just had two COs right here, this would then be a double bond. And we're not supposed to be having double bonds coming through, doing all that kind of stuff. So that's my best guess.
So basically what you're saying is if he asks this question, it's the one with the CoA and no repeats.
Yeah.
Keep it simple.
Yeah, and honestly, like, I don't have my doctorate in biochemistry, so like, I'm sure there's a biochemistry explanation for it.
I still think it's funny that he hated biochemistry when he took it originally.
Oh,
Wait,
yeah.
really? I didn't know that.
He hated it.
That's,
Then he fell in love with it because of thyroid.
Oh, yeah.
he does
The
love
thyroid.
it. Stuff.
Which, honestly, when you get deeper into stuff, next trimester, starting in Phys 2, you'll dive deeper into thyroid stuff, and then you'll talk a lot about thyroid in Tri 4 with pathology, again in Tri 5 with just like stuff that goes on with the thyroid. Like the thyroid is really, really cool. Like there's a lot of stuff going on with it, like the whole process of how it works and how it controls our metabolism and the kind of stuff that can go wrong with it is really, really cool. Okay. Which enzyme finally releases fatty acyl CoA immediately before their beta oxidation in the mitochondrial matrix? The CAT2, CAT. Go ahead. What would you say?
I was going to say CAT1. No, 2. 2.
Good, 2. Because remember we have the cytosol, we have the outer membrane, the inner membrane space right here. So there's the outer membrane, inner membrane space, and then the inner membrane. We have our carnitine acyltransferase 1 and our carnitine acyltransferase 2. As soon as we get through that second membrane, that's when our fatty acyl CoA gets transferred from the carnitine back to the CoA, and then it can immediately start beta oxidation.
So just to kind of recap and make sure I'm understanding this, the beta oxidation its whole job is to break down the acyl-CoAs into the acetyl-CoA?
Yeah.
Okay.
With the end goal of producing energy within the Krebs cycle.
Okay.
And also, even if we look at this as well, right, we're inside of the mitochondrial matrix, and the whole purpose of the Krebs cycle, what's the main thing that we produce in the Krebs cycle in order to get energy?
ATP.
Before we produce ATP, what do we make that goes to the electron transport chain?
The FADH2 and NADH?
If we notice, during beta oxidation, we make FADH2 and we make NADH. So it's literally it's all serious. So we make an FADH2 and we make an NADH, and then our acetyl-CoA goes into the Krebs cycle and pumps out more NADH and FADH2, and then all of that goes to the electron transport chain to give us more ATP. The whole purpose of beta oxidation is focused on making ATP, getting us energy. And this is why it's so much harder, like when you're trying to lose weight or anything, it's so much harder to get rid of fat because you have to burn a lot more energy in order to break down fat. Because if you think you have one triglyceride, and let's say each of these, so these are the most simple, each of these has 16 carbons. That breaks down to 8 acetyl-CoA each, plus the NADH and FADH produced for every single one of those being made. You think of how many turns of the Krebs cycle, 8 plus 8 plus 8, there's 24 turns of the Krebs cycle, plus the 777 plus the 21 extra FADH2s and NADHs that we make that also get used to make ATP. So you start to see, that's why it's so much harder to get rid of fat, because it just contains so much energy. Isn't science cool when you really break it down and understand it?
It also sucks.
It's cool. It's cool once you understand it, and when you don't have to take a test on it anymore.
It's cool when I'm not being fed through a fire hydrant.
Yeah. Okay.
I'm full of blast.
Which enzyme is the major regulatory control point for beta oxidation of fatty acids? So which enzyme is going to completely control whether or not fatty acids are going to go through beta oxidation?
Acetyl-CoA carboxylase.
I was going to say the dehydrogenase, because that has to happen first.
Look really closely. What does that say?
So acetyl and not acyl, but so it would be acyl-CoA first.
Yeah, so it's not that guy. So if we look at all of these, like pyruvate carboxylase, that's in...
Like, that doesn't have anything to do with this.
That's not nothing to do with this. Acetyl-CoA carboxylase, we don't have a carboxylase within the whole process.
So the cardinal
carnitine acyltransferase, if we're not getting fatty acids into the mitochondrial matrix, beta oxidation isn't going to happen. So that's going to be our deciding factor, our regulatory control point. If carnitine acyltransferase isn't letting the fatty acylcarnitines in, then we're not gonna be able to break them down. Okay. Which functional group of carnitine is esterified with the fatty acid in order to be transported into English, transported into the Mitochondria. Mitochondria. Hydroxyl, carboxylic, tertiary amine, or methyl. I'll be honest, I just read this question. I probably would not have gotten this right at all. The answer is hydroxyl. Let's take a look and see. Make sure we understand why that is. And that's going to be this beautiful picture, right? Nope. Gosh, I can't keep this picture for some reason. Here it is. I don't know if that is correct or not.
I had that on my quiz this week. That's the only reason I remembered the answer.
The hydroxyl one?
Yeah, I had that on my quiz this week.
It was on my quiz too this week.
And it was one of those, like, I don't know why it's that, but sure.
Which functional group of carnitine is esterified with the fatty acids to be transported into the mitochondria? Don't see anything about that in the book, per se. I'm going to see if I can get a better answer, because I don't see a hydroxyl.
It was the correct answer. That's the only reason I remembered it.
Yeah, that's the only
It
reason I
doesn't.
remembered it.
Yeah, it doesn't look like it's in the book, but
Let me
Because
here's
I
what
guessed
it's.
hydroxyl when I answered the question, and then I got it right, and I was like, oh, okay, cool.
Yeah, so I guess it, because it doesn't really show this in the book at all, but on the carnitine itself, carnitine's hydroxyl group on its third carbon allows it to form an acyl bond with fatty acids, creating the acyl carnitines. So it's not in the book as far as I can see. It might be in his slides somewhere, but if that pops up as a test question, there's your answer. Let's see if I can. Yeah, if you look at carnitine, it has that hydroxyl group poking out. Okay, we'll go with it.
Hey, Drake, which question set is that? Is that chapter?
This
Which
is
one?
fatty acid oxidation and ketones, so this is technically chapter 1, which is a doozy.
Oh, you're telling me you should see the notes I have in my margins, because Dr. Sarkar was grilling me, and in our live lecture, it was me, Kat, and Cheryl. That was it. So he treated it like a bonus one-on-one session with us, and needless to say, we all got grilled. And you want to talk about the fact that I almost cried on live? It was one of those episodes. I'm like, really?
Yeah.
And then the lady who I'm
Sarkar
housekeeper's caregiver comes in, and she's looking at me like, "Are you okay?"
What's happening? Okay. Which functional groups of the glycerol are used to esterify fatty acids in order to form triacyl glycerols? Again, hydroxyl groups.
I have no idea why, but that's always my go-to when I don't know if that's an answer. I'm like, it's a hydroxyl. That's just when I don't know. That's what it is.
It's because the way ester bonds form when an alcohol and a carboxylic acid react together. Alcohol ethanol is an OH.
Mhm.
So ester bonds are formed with hydroxyl groups. So that's why, and that's why up here as well. Esterified, ester bond, hydroxyl group. Which means, I think, if I'm not mistaken, this question, if this was changed, which functional group of carnitine, if it was instead changed to which functional group of a fatty acyl is esterified, I'm fairly confident that the answer would actually be a carboxylic, because it's an alcohol and a carboxylic acid undergo a condensation reaction. So I would probably jot that down. So if it's a carnitine on the carnitine side, it's a hydroxyl being esterified. If it's on the fatty acyl side, it's a carboxylate. Sometimes with these questions, he'll take the same question but just flip one word and make it like the reverse.
Hey Drake, remember we were talking about the fatty acids earlier in the chapter about like the whole list of them that we needed to know?
Yeah.
I found it. It's on page 19 of chapter 1. Bless you, Lily.
6, 7, 8, 9, 10, 11, 12, 13, 14. Chapter 1.
Yep. At least in our book it is.
He might have updated the book.
I have
might
the
not-
updated one.
I might not have the most updated one.
But if you have it, Liz, it's page 19.
Okay.
There's 5 of them. It's linoleic, arachidonic, linoleic acid ALA. I can't pronounce EPA and DHA.
Can you take a picture of that and just send it to me
Yep.
so that I can make sure that I have that? Okay. Question 32. Which molecule is required to transport fatty acids with a chain length longer than 14 carbon atoms across the mitochondrial outer membrane for their beta oxidation? This is our wonderful carnitine. If it's less than 14 carbon atoms, it can just pass right through all by itself.
That's what I was about to ask. Like, why is 14 the magic number? Okay.
Yeah, once it gets too large, because if you think the membrane is a phospholipid bilayer membrane that's in the mitochondria, or it's like those membranes are phospholipid bilayers. And remember when in Biochem 1 when Dr. Sarkar said like dissolves like?
Mm-hmm.
Yeah, so fats can pass through the phospholipid bilayer. But once they get to too big of a size, it becomes too difficult to get through, and then they need help. Okay. Which of the following compounds can activate the hormone-sensitive lipases during the cleavage of fatty acyl groups from the triacylglycerol molecules? Before we keep moving on, let's talk about hormone-sensitive lipase. The hormone-sensitive lipase, specifically its job, is it's an enzyme that's going to mediate the breaking down of the triglycerides to provide the free fatty acids in the hormonally controlled side of things. So if we look at all of these options, we're going to look at this in the hormones specifically. It's a hormone-sensitive lipase, so hormone-sensitive. We look at these two immediately, those aren't hormones. And we look at estrogens versus norepinephrine. We say, okay, of these two, which of them are going to encourage the breakdown of triglycerides in order to give us more energy? Estrogens or norepinephrine, aka noradrenaline. It's going to be our norepinephrine because we need energy when we have adrenaline going on. We want to break stuff down and get things rolling so that way we can fight or flight or do whatever we got to do.
That makes sense.
This is also important to remember. There's a little note that the heart mostly uses fat to operate. Does that ring a bell? There was like one little portion that mentioned that in the book. So the heart itself, especially when you get norepinephrine, the heart starts to beat faster. And so we need to break down more tissue in order to, more fat in order to continue to provide energy that the heart needs. Which of the following compounds can be formed as ketone bodies in severely starved condition? I think this is the third time this question now has been asked.
Yeah, I'm pretty sure.
All of the above.
Yeah. Just acetone. I hate when it says all of the above and like it's mixed.
Yeah, that bothers me.
Which of the following compounds is an inhibitor of carnitine acyltransferase 1? Remember earlier we talked about and we mentioned that carnitine acyltransferase 1 is going to be in control, be regulator of beta oxidation. Okay?
Yes.
So what goes back to inhibit that is going to typically be kind of like either the end products or the opposite, the product or the reactants of the opposite reaction. Okay. So for example, best answer choices here, if we're guessing, would be acetyl-CoA or malonyl-CoA, because we're trying to create acetyl-CoA, and we're trying to create acetyl-CoA inside of the mitochondria in order to make the energy, and that's beta oxidation, which connects the carnitine acyltransferase 1. But malonyl-CoA, this is going to be kind of a little future knowledge. Malonyl-CoA is involved in the synthesis process of fatty acids. It's involved in the synthesis of fatty acids. And also that's occurring in the cytosol. Remember, carnitine acyltransferase is on the, transferase 1 is on the outer membrane, so it's not going to interact with the acetyl-CoA because the acetyl-CoA is on the inside in the matrix. So our best answer choice here is the malonyl-CoA, because, and that's a little bit, if we were doing this right when we were reviewing chapter 1, wouldn't be a super fair question, because that's a little bit more future knowledge of chapter 2 with the biosynthesis stuff. And we'll loop back around to that. Is that okay?
Yep.
That's fine.
Which of the following condition or conditions can generate ketone bodies? Severe starvation, very low levels of available oxaloacetate, or untreated diabetes mellitus. Or as Dr. Perryman would say, diabetes mellitus.
Yes, you would.
I love Dr. Perryman. Answer this one's going to be all of the above. I really hope you guys get to have Dr. Perryman for systems pathology and farm talks.
I hope he doesn't retire.
He's one of my favorite professors.
He's fantastic. I got to have him for AMP too, and I was like, I love you.
He's one of my favorite teachers. Such a good guy. Okay. Which of the following is a major carrier of free fatty acids in the plasma? Plasma, we're talking about blood. Right? What in the blood helps to carry around some of those free fatty acids?
Albumin.
Yeah, our serum albumin. Which of the following molecules is required for the activation of fatty acids for their beta oxidation? Oh, I get it now. Earlier I was like, hey, where the heck is the ATP? It's in the activation in that acyl synthetase. Acyl-CoA synthetase uses ATP to bind that CoA to activate. There we go. The fatty acid for beta oxidation. That's where that ATP comes into play. That's where it's important. Cool. Next question. Which of the following nutrients would yield maximum amounts of energy upon complete oxidation in humans? 1 molecule of vitamin A, 1 molecule of albumin, 1 molecule of glucose, or 1 molecule of palmitic acid? What do we think?
Not gonna be albumin because that's not gonna. That just doesn't make sense. It's not gonna be vitamin A.
So which does more, glucose or a fatty acid?
A fatty acid.
Boom, fatty acid. Do you guys remember the trick? Remember this is just a cell vitamin A. Do you guys remember the word trick to remember all of the fat soluble vitamins?
I do not.
It's A, fat, dip.
That's right.
Vitamins A, D, E, and K are fat soluble. Which of
In
the
high school,
following?
I was gonna say in high school it was always eat a dick.
There you go. That works too. Which of the following?
DAK.
Eat a dick. There we go. Either of those works great. Which of the following pairs of molecules is used as oxidizing agents during beta oxidation of fatty acids? Remember, oxidizing agents, their job is to get reduced. So which of these are going to be the oxidizing agents?
Sorry for the dog.
NADH and FADH2.
So we look at those, right? This kind of goes back to in Biochem 1, where I warned you guys about these kind of questions. So the answer is going to be the FAD and NAD+, because NADH and FADH2 have already been reduced. So they're already used up.
That's right.
So because of that, it's not what we're looking for. We're looking for the pre-reduced forms, the FAD, the NAD+, those are our oxidizing agents.
That's right.
So just be careful with that. This question's, I bet you this question's going to pop back up because he likes these kind of questions. He liked them in Biochem 1. He'll probably throw one just like this on for Biochem 2, this upcoming test. Which of the following pairs of molecules could be the end products of complete beta oxidation of an odd chain fatty acid?
What does that mean?
Odd chain fatty acid, that means like palmitoyl-CoA has 16. It's like as if one had 17 instead.
Okay.
so there's not an even number of carbons to break down into acetyl-CoA.
Gotcha. Okay. So it's not going to be B because you can't get to acetyl-CoA. You can't get to 2.
So with this one, we haven't gotten to HMG-CoA stuff yet, so we're not going to worry about that. Malonyl-CoA is one of the typical options, but butyryl-CoA, not, because this is a 3-carbon, and I think this is a 4-carbon, so that doesn't make sense. So the answer is going to be B. Propanol-CoA is also a 3-carbon. Another potential answer choice that he could have had would be that malonyl-CoA that can also be produced. So acetyl-CoA and malonyl-CoA would be another potential answer choice for this question. Both of these, the propanol-CoA or the malonyl-CoA, both of those would be correct. Just know that we have one has to be a 3-carbon that's left over because of how many carbons that there were. Which of the following products of the acyl-CoA dehydrogenase catalyzed reaction occurring during beta oxidation of fatty acids? So right off the bat, we look at this acyl-CoA dehydrogenase catalyzed reaction. So this right here, what number step is this in the beta oxidation?
1.
This is our first step. So occurring during the beta oxidation of fatty acid donates electrons. So which of the following products donates electrons to the mitochondrial respiratory chain? So which of what essentially is asking what's going to be created in that first step that goes off to the electron transport chain? So we look at these immediately. FADH2 and NADH are the only ones that go off to the electron transport chain, so we can cross out those other 2 answers. So which of these is used in the first step, the first dehydrogenase?
It's FADH2, I think.
Yeah, it is. Good. FADH2 is used in the first dehydrogenase. NADH is part of the second dehydrogenase. This one right here, the hydroxyacyl-CoA dehydrogenase. Beta hydroxyacyl-CoA dehydrogenase. Almost done. We're almost there, guys. Which of the following represents the correct sequence of events in a cycle of beta oxidation beginning with a saturated fatty acyl-CoA? So saturated, remember we talked about saturated. What does saturated mean?
Like all of the carbons are covered with hydrogens, basically.
Yeah, so there's no extra steps that we have to do in order to prep it in order to break it down. So we look at this. What are going to be our steps? So our very, very first step, remember what's our first enzyme that we use?
The acyl-CoA dehydrogenase.
Acyl-CoA dehydrogenase. And what do we use as a coenzyme to make that happen?
FAD.
FAD. So immediately we look at our answer choices. Correct sequence of events. FAD coupled oxidation. FAD coupled oxidation. Bam. 2 answer choices. Gone. What's our second step? After dehydrogenase, remember what's our next step?
It's the
NAD.
because the hydrogenase is next, right? Or
yeah, the hydration.
Yeah.
Hydration is going to be next.
Okay.
So we have DHTD, so it's dehydrogenase, hydration, biolase, and then another dehydrogenase. So our answer choices, FAD coupled oxidation, and then a hydration.
Remind me, because it's been in a couple questions and I'm like, wait, I don't remember this. Remind me what cleavage is again.
Splitting, cutting.
Okay.
Think of it as a cleaver, Liz.
Cleaver. Oh, that makes sense. Got it. Cool.
Not all this crap makes sense to me, but I can make it make sense in my head.
I mean, yeah. That's how you get through, right?
Do what you gotta do.
Why would that NAD in that question not be last?
Because I've been saying it wrong. I got it wrong in the very beginning.
Okay.
Sorry, guys. DHDT. It's dehydrogenase, hydration. That's on me, guys. That is called It Is Almost the Weekend, and I am a sleepy boy. DHDT. DHDT. Which then that kind of makes D hot. Makes more sense. Like the second D kind of looks like an O if it's capitalized.
Oh, yeah.
That makes more sense. We got it right last week. This week, I'm just a silly boy. Okay. Glad we caught it, finally, after 43 questions. Oh, we only looked at that whole process like 20 times. Nice. Okay. Which of the following statements applies to the beta oxidation of fatty acids? NADP plus is the electron acceptor. Malonyl-CoA is used as the 2-carbon unit donor. Carbon atoms are removed from the acyl chain one at a time. The products of beta oxidation can directly enter the citric acid cycle for further oxidation.
D.
Yeah. These first two, specifically these first two, are talking about synthesis. And then one at a time, wrong. It's two at a time because they're taken off as acetyl-CoAs. Which of the following statements is true during beta oxidation of 1 mole of palmitic acid? You need to remember palmitic acid, that it's 16(0). Super important. You'll get asked a ton of questions about palmitic acid, I promise. So how many moles of ATP, not of ATP, of acetyl-CoA or NADH or FADH are formed? Let's start with the easiest one. How many, if we have 1 palmitic acid, how many acetyl-CoA are we going to make?
I don't know. While y'all were going through that earlier, I was very confused, but so how do you figure that out? Like, how do you know?
So remember, if there's 16 total carbons in palmitic acid, and each acetyl-CoA is made up of 2 carbons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? 16 carbons. Every cycle that we go through, we cut off 2 carbons. So there's 1 acetyl-CoA made. Second cycle, and we make another acetyl-CoA. Third cycle, we make another acetyl-CoA. Fourth cycle, we make another acetyl-CoA. Fifth cycle of beta oxidation, we make another acetyl-CoA. 6th cycle, we make another acetyl-CoA. 7th cycle, because we only have 4 left, we make 2. So we have 7 cycles.
And that's what you were talking about with it's the carbons divided by 2 minus 1 is the cycles.
Exactly, yeah.
Okay.
And we make 1, 2, 3, 4, 5, 6, 7, 8. 8 acetyl-CoAs.
The number of carbons divided by 2?
Yeah, exactly. If it's an odd number, so like let's say we have 17, 0, we would make 7. Let me type it because it'll be easier. We'll make 7 acetyl-CoA and 1 either malonyl-CoA or the propionyl-CoA, because one of those has 3 carbons. So 7 times 2 gives us 14. 14 plus 3 gets us to that 17.
That's where the odd chain question, that one comes in.
Exactly. Yeah, that's where that odd chain stuff comes in.
Okay.
So, and then we can also do some other math. So with every single cycle, so 7 cycles, with every cycle, we also produce 1 NADH per cycle. So that would give us 7 cycles, 7 NADH, and also 7 FADH2, right?
Mm-hmm.
So we look at our answer choices. Any of these potentially could be good answer choices. That in the beta oxidation of palmitic acid, there are 7 cycles. We make 8 acetyl-CoA. We make 7 NADH, and we make 7 FADH2. So we look here. We don't make 1 mole. We make 7. We don't make 5. We make 7. We do make 8 acetyl-CoA, not 2.
That makes more sense now.
Good. Woohoo! Last questions. Which of these is able to cross the inner mitochondrial membrane during beta oxidation of fatty acids? Fatty acids having more than 20 carbon atoms that are unsaturated. Remember, we talked about the limit being how many?
14.
Being 14 carbons. Fatty acyl carnitine. Fatty acyl carnitine, we're going to keep that one in the running because that's literally its whole job is to cross that mitochondrial membrane. Acetyl-CoA, when we talk about acetyl-CoA, that's formed and kept inside. The answer is supposed to be fatty acyl carnitine. I think this is a little bit of technical, because technically acetyl-CoA in different ways does. I guess it doesn't cross directly. That's probably what it's getting at. Fatty acyl carnitine is in the form that it can pass as it is. That's my guess why that is, but stick with the stuff that we're reviewing currently. If it's another answer choice from previous stuff, go with whatever's most recent you've learned most recently. What portion of a diacylglycerol 3-phosphocholine contains the largest fraction of the biochemically available energy? That looks like a really confusing whole thing. A lot of really, really big words. It's referring to, where's the picture? It's referring to this guy. Where it has the glycerol, it has the phosphate, it has the fatty acyls, all that kind of stuff, okay? That's just the big fancy name for that guy. So with all of those, which contains the largest amount of energy? The glycerol portion, the head group, the phosphate portion, or the fatty part? the fatty part contains the most energy. And finally, we're finished with this section. Woo!
We did
That
it.
was a lot. On this material that we just covered, compared to how we started, how do we feel now?
Better.
Good. I think the next one has just as many questions, maybe even a couple more. Yeah, it has more questions, so we'll get to that. We'll probably try to focus on getting through this one next Tuesday. And let me look at the other two real quick to see how much is in them. I don't think that they're as big. That one's still pretty. Jeez. They went ham with the questions on these units. Okay. Okay, we will get through whatever, as much as we can get through for next week. I'll look at schedule-wise and stuff and see if it's possible to do either another session or if I can get a recording going through these or something to try and get as much of them as I can. I do definitely feel like doing it live like this and meeting up is more beneficial than me just kind of going through them.
This is definitely the most helpful thing for me, for sure.
Yeah, so we'll plan for sure next Tuesday doing it. If possible, kind of like either Tuesday during the day or Monday or something, if you can rewatch my recording of chapter 2 of biosynthesis. That way, hopefully, we can be a little bit more fresh and we can kind of run through this a little bit. Honestly, I'm going to say we'll probably just get through this one. And then we can take a look and see if potentially Wednesday, if people are down to meet again and crush through the next one or both of them. And that'll put us at a position where we're caught up. And then, because it was on me the first couple weeks of the trimester, I would drag my feet setting up these meetings, and so we got a little bit behind. So
Hey Liz, I can always send you my login and you can try to log in and take the practice ones if you want.
I bought the book for this one, so I have got mine.
Nice.
we go ahead and stop the recording.